Morning.
Good morning. Today, okay. So you can wear a Santa Claus hat if you have one. Okay. Okay, here we go. So this is 5.1 area and distance. Okay. So okay, I can see my screen, right? Okay. So we're going to talk about area and distance. Okay. So if we have a continuous curve, okay, that means there's no break on this interval a to b, then what will be this area? Suppose this is a positive function. What will be this area under the curve? So today we're going to investigate on that, okay? So first of all, say this is a continuous curve, okay? X squared, this function here is the x squared function. From 0 to 1, the green shaded area will be the area under the curve, right? Now, we don't have a formula for this area right now, okay? We know a formula for rectangle, length times width, give me the area, okay? So what we do over here is we're gonna break it down uh, into uh, different slices, and each slice here, we're gonna approximate that using rectangle. So over here, I slice it, okay? So from 0 to 1, I divide it into 4 subintervals, each one with equal width, delta x. And then for each slice here, I'm going to approximate that by one rectangle, okay? And when I sum up those rectangles, the area for those rectangles, that will be an approximation to the area under the curve, okay? Now, if I use 4 of them, it looks like it's an estimate, it's an approximation to the area, but it's not a very good approximation. I can improve that by divide this interval into subinterval with smaller width, okay? So make delta x to be smaller. And I got this. I think the sum of those rectangle, the area of the sum of those area of the rectangle will be a better approximation. Now I actually decrease delta x more. Okay, I get more rectangle, and the sum of those will be a better approximation. Okay, and then over here I even divide divide this interval into more subinterval with equal width. So make delta x to be even smaller. It looks like the sum of those rectangles are getting very close to the area under the curve. Okay, so you can imagine this process right here. Okay, continue this way. So and later we're going to divide the area as the area under the curve as the limit of those sum of those rectangles as you make this delta x to be smaller and smaller, and then okay, all right. So this is the idea, okay? So over here, we're going to subdivide this region over here into n stripes with equal width delta x, okay? So delta x is a width for each subinterval. So delta x will be the total length, which is b minus a, divided by n, because we divide that into n subinterval. So b minus a divided by n, that's delta x. The second step here, we're going to approximate each stripe with a rectangle. Say, like this stripe right here, underneath the curve. We're going to approximate that by this pink rectangle over here, okay? And we're going to use the value of the function at the y point as the height of this rectangle. So for example, in this rectangle, I take this y point and use this y coordinate of this y point as a height for this rectangle. So the height here times the width here give me this area for this rectangle. You see, I take the y point, and using that height for the length of the rectangle, and the width will be delta x. So the first rectangle over here will take this, the y coordinate at this point, which is f of x1, and then times the width here will be delta x. So f of x1 times delta x give you the area for this first rectangle. f of x2 times delta x give you the width, give you the area of the second rectangle, okay? And the last one over here, f of xn times this delta x, that's the area for the last rectangle over here. And notice I divide this interval a to b into n subinterval. So this a here corresponds to x0, x1, x2, and then the last one, the b here is xn, okay? And then you're going to sum up those rectangles, right? Sum up those rectangles. So you sum this up, okay? To sum this up, we have this summation sign right here, okay? Now, suppose you haven't seen this before. Let me explain that to you. This is called the sigma notation. So you sum this, all of this up. See, there's a pattern. All of them have delta x. So put delta x over here. Every term here is actually f of x, x1. This is f of x2. This is the last one is f of xn. So the index over here changed from 1 to 2 to 3 to 4 all the way to n. So we're using I over here. Okay, so we use I over here to stand for the index. Okay, and the I here start from 1 and end at n. So I go from 1 to n. And from 1 to the next one, you always increase the index by 1. Okay, 1 and then to 2 to 3 and all the way to n. Okay, and then you stop when you reach n. Okay, so and this is the sigma notation here, means you're taking the sum. Okay, you're summing f of x1 delta x and then plus f of x2 times delta x, and then you put this f of x3 times delta x, etc. Okay, so this tells us a sigma notation tells us to add, and this one down here tells us we start I here go from 1, and this one here we this tells us to end with I equal to n. Okay, so this is just a notation for the sum over here. Okay, now we're going to define the area under the curve as the limit of the sum. Okay, now here I use a R over here. This is what this R here stands for using the y endpoint as a height for those rectangle. Okay, using the y endpoint, the y coordinate of the y endpoint as a height of those rectangle. And I have n of those rectangle, right? I have n of those rectangle. So I call this Rn. So it is sum of those, the area of those n rectangle using the y endpoint for the height, okay? The y coordinate y endpoint as a height, okay? So we define the exact area, the area under the curve as the limit of this, okay? And as you see from the diagram over here, when you let n go to infinity, okay, those Rn is going to approach to the area under the curve, right? Okay. Actually, yeah, you can see over here, okay? So this is a diagram. Oh, okay. Now, instead of using the y endpoint, okay, so over here, we're using the y endpoint and using the y coordinate of that for the height for each rectangle. We can also use the left endpoint. So over here is an example using the left endpoint. So we divide that into 4 subintervals, but this time we take the left endpoint for the y coordinate for the endpoint for the height, okay? And then we found the area for each rectangle. Now notice that here, the leftmost rectangle has collapsed because the height for this rectangle it is 0. But that's okay, okay? That could happen, okay? So now notice that what happened here when you let n here increase, then the area for those n rectangle is also getting closer and closer to this exact area under the curve, right? So you can use the right endpoint or use the left endpoint. You can also use a middle point. So for each subinterval, instead of taking the left endpoint, the right endpoint for the height, You can also take the middle point and using the y coordinate, the middle point over here, okay, for the height. Okay, and then we find the area for each rectangle. Okay. Well, also you can use any arbitrary point. For example, over here on the first subinterval, I pick x1 to be this. So, and then pick x2, because x1 is reserved for this end of this subinterval. So this, the x coordinate for this, I'm going to use x1 star. The star over here just indicate that it is a sample point. Okay, so the star here says that this is a sample point in the first subinterval. So x1 star is a sample point in the first subinterval. x2 star is a sample point in the second subinterval, etc. Okay, so do not be intimidated by those notation. Okay, the star just means it's an arbitrary point, a sample point in this subinterval. Okay, and then we use that point, the y coordinate here as a height, and then times the width, which is delta x. So the y coordinate for those sample point right here. Okay, the y coordinate, so f of xi star, that corresponds to the y coordinate of this point, and you times the width, which is delta x. So that will give you the area for one rectangle, right? And now you're going to sum up n of them. So I go from 1 to n. So that will be the sum of those n rectangle. This is called a Riemann sum. Okay, Riemann sum right here. Okay, now you take the limit as n go to infinity. Okay, just like what you have done over here. You let n go to infinity. That will approach to this Riemann sum is going to approach to the exact area under the curve. Okay, question?
Not yet.
Okay, that's good. So using the right end point, that's Rn, that's the sum of those n rectangle. Using the left end point, the sum of those n rectangle is called Ln. Using the middle point, the sum of those n rectangle is called Mn. Is any sample point over here? Okay, this is a Riemann sum. Okay. Now this Riemann sum over here is going to, okay, let me give you this. Okay. Okay, now I'm going to ask you in the homework. Okay, so some people, you're going to be asked this question. So suppose you have an increasing function. Okay, if you're using the y endpoint for the height of those rectangle, so Rn will be an overestimate or underestimate of the area under the curve.
Underestimate.
Using the
Over.
y endpoint.
Using
Under or overestimate?
Over.
It's an overestimate because the y endpoint is the highest point in the each subinterval, right? So when you use the y coordinate that, then this rectangle is going to above the stripe right here, right? So you have this extra area above the curve. So it is an overestimate. So that will be overestimate, okay? And if you use the left end point, the left hand point is the lowest point in each subinterval. So that will be an underestimate, okay? Okay, now vice versa, if you have a decreasing function, using the y endpoint, that will be what? Under or overestimate?
Under.
Under, yeah. Underestimate, okay, so that will be underestimate. And using the endpoint, that will be overestimate, okay? Okay, now in this example, we are trying to use 4 rectangles to find a no estimate. All right. Okay, so We use for rectangle to find a lower estimate and an upper estimate for this area under this curve. So they give you the curve, and I also give you the coordinate for those endpoints right here. Okay. So first, I'm going to have, let's try to find a lower estimate. Okay. So what's delta x over here? What's the width for each subinterval?
2.
2. 2, right? Okay,
Yep.
you got it. Okay, so that is 2. Okay, so lower estimate. So using the left endpoint or the right endpoint? It's
The
an
left.
increasing function. So we take the left endpoint. Okay, so it will be L. I'm using 4 rectangles, so L4. Okay. And then this is L here stands for left endpoint. Okay. Now that's equal to, okay, the first rectangle over here, the left endpoint, the y coordinate is 4. So we have 4. Delta x over here, it is equal to, there's a different color, equal to 2. Okay, so times 2. Okay, maybe I just use the color times 2. Okay. The second one over here, the second rectangle, the left hand point is 4.8. The y coordinate is 4.8. So 4.8 times the width, which is 2. Okay, what about the next one? 5.1, right? Times 2. And then the last one will be 5.3
times 2.
times 2. Okay, so I'm using 4 rectangle. And I'm using the left hand point for the height. Okay. And because this is an increasing function, so the left hand point here is the lowest point in each subinterval. So this will be a lower estimate. And if I sum this up, I got 68.4. So the lower estimate for the area under the curve will be this. Okay. What about upper estimate? Upper estimate. Okay. So upper estimate. This time I will use the right endpoint. And similarly, this time on this subinterval, I will take the y endpoint. The y endpoint is this. So we use 4.8 for the y coordinate. We use 4.8 as the height of that rectangle. Okay. And then times 2. And then 5.1 times 2. And then 5.3 times 2. And also 5.5 times 2. Do the calculation, so that's equal to 41.4. So this is an overestimate, this is an underestimate. So the exact area and the exact area under the curve is going to be between these two numbers. Okay, somewhere between these two numbers. So you can try to, maybe you can take the average of these two and to approximate the area under the curve. Okay. Now the next example is the cosine function. Okay, so this is the curve for cosine function from 0 to pi over 2. And they ask you to try to estimate the area under the curve. Okay, how about we use, let's try to use 4 rectangle to approximate that. Okay, so I'm going to divide this. Okay, so I'm going to divide this into 4 equal parts, into 4 subinterval, each with equal width. So that will be What's delta x? Can someone tell me what's delta x?
Pi over 8.
Yes, pi over 8, okay? So delta x over here will be equal to, the width for this interval is pi over 2, and we divide that into 4 subintervals. So that will be that will be equal to pi over 8, right? So pi over 8 is this, okay? And then this is pi over 8. So the next one here will be pi over 4. And you keep on adding pi over 8. So this will be 3 pi over 8, right? Okay, and then pi over 2. And then you're going to use, so you're going to divide. Okay. Let's use the y endpoint, okay? So let's think about R4. I use 4 subinterval. So I use 4 rectangle. And this means the y endpoint. Okay. So that's equal to, what does it equal to? Using the y endpoint, so this will be the area and for the first rectangle, right? And then this is the area for the second and third. And the last one over here collapsed though, because the height it is 0, okay? So for the y endpoint, let's find the y coordinate for each y endpoint. This is cosine of pi over 8, right? Okay. It's cosine pi over 8. And this one over here is cosine of pi over 4. This one over here is cosine of 3 pi over 8. This one over here, the y coordinate is cosine of pi over 2, which is equal to 0. So it collapses to 0, okay? Delta x over here is equal to pi over 8. So each one here is going to be pi over 8. So all of this pi over 8. Okay. Okay. Now, if I use, so when I find the sum of those 4 rectangles using the y endpoint, so we have cosine of pi over 8 times the width, which is going to be pi over 8. Okay. And let me put this way. Adding cosine of pi over 4 times pi over 8 plus cosine three pi over 8 times pi over 8 times the width. And then the last one is cosine of pi over 2, then times pi over 8. Okay. Now cosine of pi over 2, it is going to be 0. Okay. And then you can use a calculator. Okay. So all of this. So you use a calculator. Whatever number you come up with, okay, you can do that at home. Is it underestimate or overestimate?
Under.
Under.
Underestimate.
Yeah.
Okay, because it's a decreasing function. So this one here will be an underestimate for the area under the curve. So that's what I'm going to do for homework. Okay. Okay. So the next one, the distance problem. Let me briefly go over this. Okay. Now we know that distance is rate times time when you travel at a constant rate. Okay. Or this is an average rate. Okay. Rate times time. Now suppose the odometer on your car is broken and we want to estimate the distance driven over a 30-second time interval. We can take the speedometer reading every 5 seconds. You might wonder, why do you want to do that? Okay. Okay. So, and then you read it every 5 seconds. Okay. So every 5 seconds you read that reading. Okay. Now, what happened over here? Okay. Now remember, for this one, this formula over here. Okay. Distance equal rate times time. The rate over here, it is the constant velocity or average velocity, average rate. Okay. Now, over here, now you read the speedometer every 5 seconds. Okay. And you got those number. Okay. Now, in order to have the time and velocity in consistent unit, let's convert the velocity reading to feet per second. And then you're going to convert that mile into feet per second. Okay. So they did the conversion for you. Okay. Using this. Okay. So every 5 seconds you read the reading, and this is in feet per second. So that will be the velocity. Okay. At that time. Okay. So during the first 5 seconds, okay, so notice that the delta t over here, okay, the delta t over here, it is going to be 5 seconds. So every 5 seconds you take the reading, right? So the time interval is going to be 5 seconds each, okay? Okay, now what you're going to do here is, okay. So during the first 5 seconds, the velocity doesn't change very much, right? Because the time is so short, only 5 seconds. So the velocity doesn't change that much, okay? So you can think about, you can estimate the distance traveled during that time by assuming the velocity at this reading is going to be constant. So during that time interval, we assume that to be constant. Because time interval is so small, 5 seconds, it doesn't change much. Let's assume that it's a constant, okay? So we can estimate that, okay? Okay, so, and then you're going to take the velocity during that time interval to be the initial velocity, which is the 25 feet per second. And then you're going to times the time, which is 5 seconds. Each time interval is 5 seconds. So rate times time gives you this 125 feet. So the first 5 seconds, you travel about 125 feet. And you do the same with the second one. So you take the reading over here, okay? So in the beginning of the time interval, 31 feet per second. And you times the time interval, which is 5 seconds. So you got this. And continue this way, okay? You can sum up the distance, you can sum up those, you can sum up the estimate for the distance travel in each sub-interval, each sub-time interval, okay? And it turned out to be 1,130 feet, okay? Then that will be an estimate of how much distance you travel during this 30-second time interval, okay? And then instead of using the left endpoint, you can also using the right endpoint. Okay, so each time interval, you can take the right end. So you can use the velocity at the end of the time interval times the time interval 5 seconds. And then you will do the similar process and you end up with this number over here. Okay, this number over here. Okay. So if you want a more accurate estimate, we can take the time interval to be even smaller. Instead of 5 seconds, we can take every 2 seconds. okay, or even every second, okay. Now the point over here is that we're trying to, you're trying to get an idea, okay. The idea here is, suppose this is a velocity function, okay. This is a graph of velocity function. You can use the velocity, okay. So the problem we have this done over here is this. We use the velocity in the beginning and you times the time interval over here. Okay. So the velocity in the beginning over here, it is what? It is V0, right? And you times the time interval, which is 5 seconds, okay? And then later you take the velocity over here, you times the time interval, which is 5 seconds again. Oh, V of 5, okay? And then we continue doing this, okay? And then the last one here is the velocity at 25 seconds. And then you times the time interval over here, which is 5 seconds. And then it turned out to be 1130 feet, right? We did that already, okay? So you see this delta T over here is equal to 5 seconds. So that's why the 5 here and also here, okay? Okay, so using the left endpoint. Now you use the right endpoint. So you take the reading, the speed of the car at the end of this each time interval, okay? So this time we have, at this time interval, ended at 5 seconds. So V5, we use V5 as the average velocity, okay? And we times this by 5. And then similarly, V10, we times it by 5. Continuing this process. What's the last one? Can someone tell me what's the last one?
V30.
Yeah, you got it. So it is V30, the velocity at 30 seconds, and you times 5. Okay, and we did. We do the calculation, so that is going to be 1210 feet. Okay. All right. So, and then you can make the time interval to be even smaller and smaller, to be maybe every second. Okay. Okay. Repeat this process. Okay. Now it's similar to our Riemann sum. Okay. When you make the time interval to be even smaller and smaller, then the sum of those rectangles is going to be closer and closer to the area under the curve. So you see this one here actually corresponds to the area of this rectangle. This corresponds to the area of this rectangle. This corresponds to area of this rectangle. So this is actually the sum of those area under the, it's the sum of those, and it's the sum of those 6 rectangles using the left hand point. This one here is actually correspond to the sum of those rectangles using the right endpoint. Okay. Now, when you make the time interval to be even smaller and smaller, then the area under the curve will be closer and closer to. Then the sum of those rectangles will be closer and closer to the area under the curve, and the sum of this will be closer and closer to the exact distance that the car traveled. So you see that the area under the curve is actually correspond to the distance that the car traveled. So the main point that they want to show you is this sentence here. The distance traveled is equal to the area under the graph of the velocity function. Okay, so what does it mean? Okay, so over here, say this is for the time. Okay, so this is for the time. And if the time go from A to B, okay, and you have this velocity over here. So this is the velocity function, and that's a graph. Then if you try to find this, so this area under the curve over here, this highlighted yellow part right here, this area over here is the distance traveled. So corresponding to the area under the curve. Okay. Now, which makes sense. Let's try to think about when the velocity is actually a constant, right? So suppose we have a constant velocity, okay? Then what happened over here from A to B? The time go from A to B. Then the distance traveled over here will be the area under the curve will be this part right here, right? We'll use the velocity times the time elapsed, okay? So velocity times the time that passed will give you the distance traveled, okay? So that's the end of 5.1. Are you guys good?